In the previous lecture, we introduced the notion of graphs, and then we defined when are two graphs same. We talked about what is the isomorphism between graphs, and then we saw a theorem called as Euler's theorem. We did not prove this, so that is the first thing that we will do today. So, Euler's theorem states that a connected graph has an Eulerian circuit if and only if the degree of every vertex is even. Okay, so, Eulerian circuit was a walk in the graph where no edge is traversed twice and every edge is traversed exactly once. For example, if we consider the following graph, this graph will not have an Eulerian circuit as per the theorem, because if you look at these vertices, they all have degree 3. But we can convert them into, if we modify the graphs, this particular graph, this will have an Eulerian circuit because the degree of every vertex is even. I am just writing down the degrees of the vertices, these are not the vertex labels. Okay. So, this graph will surely have an Eulerian circuit, and we will in fact construct one such and convert that into that construction into a proof. So, let us say we start from this particular vertex. Okay, so, if we went about in this particular fashion, there are lots of edges which are not traversed. We can separately look at them. This is yet another one. So, we drew this as, we traversed this graph by means of 3 cycles. We could have done that more systematically. We could have started from here, and at this point we can just come back here, or again we can take this, come back here and then do this. Okay. So, that gives us an Eulerian circuit. So, the method by which we drew looked like arbitrary, we just arbitrarily traced the edges. We can essentially convert that method into a proof of our theorem. So, we will do that first thing. Okay. So, the key idea is, since every vertex has degree even, if you enter any vertex, you have to obviously leave the vertex. Okay. You will never be stranded at any particular vertex. So, let us say we are randomly moving from one vertex to other, and we are not being particularly clever about which is the outgoing edge. For example, if we come to this particular vertex, okay, one of the edges have been used, but the fact that the vertex has an even degree means that there is at least one leaving edge. Okay. So, for every vertex, if we start at any arbitrary vertex and keep on moving, that is tracing edges, the only requirement or the only restriction that we will impose on our walk is that we won't take the same edge twice. Now, if we do this, what happens, we can write the following statement. If we walk in an arbitrary fashion, we will always have an outgoing edge at every vertex. Okay. Of course, there is a particular case that we have to be careful about. Suppose we come back to a vertex and all the edges have been exhausted at that point. So, you start at some place and you move around and finally come back at this place, and suppose this had only exactly 2 vertices, then what will we do? Okay, so that is one situation that we have to be careful. It could be the case that once we did this, there are other edges lying outside of this particular circuit. What we have ruled out so far is that if we reached some particular vertex after a lot of travels, okay, either it is one of the starting vertices, we could reach at the starting vertex. If you are at an in-between vertex and you have no edges to move, that means you have come there some number of times and you have left that vertex one less time. Okay. So, formally we can say this as the as following: if we are, let us say, stranded, suppose this was a possibility that we were stranded, then we have entered the vertex, the stranded vertex, x times and left it only x minus 1 times. Okay. The starting vertex is different because starting vertex we never enter, we just, I mean, we just leave the starting vertex. Okay. So, but for every other vertex you are entering that from some other place and then you are leaving it. So, you would have left it one less time than you have entered. So, the total edges of that particular vertex which has been traversed is equal to, that accounts only for 2 times x minus 1 edges, okay, and that is an odd number of vertex. And since we assume that every vertex has even number of even degree, we will never be in such a situation. Okay. We could of course start at a vertex and then come back to the same vertex. Okay, that is a possibility, and at that point it could be that there are other parts of the graphs which are not traversed. Okay. But here we can use induction. Now, by virtue of this graph being connected, okay, we can say that if there are other edges which are traversed, which are left behind, then there should be some connection to that, to the left out edges, and what we can do is the first point from where there is an edge which is not accounted for. So, look at this path and look at the first vertex which has an edge which is not used. We could start there and then continue, and we must essentially come back somewhere here. Okay. We will never be stranded. The only way we can be stranded is if we had come back here. Okay. So, we can just traverse along the particular path, complete that cycle and then continue on the original cycle. So, this can be done inductively, and therefore, that will guarantee that if the degree of every vertex is even, then we will automatically have an Eulerian circuit. The other part is simpler. If we had some vertex of odd degree, then there are no Eulerian circuits. This can be seen because if you look at the Eulerian circuit goes through every edge. So, if you look at any particular vertex and count the edges, it is the Eulerian circuit has entered every vertex and left every vertex. Okay. The number of times it is entered is exactly equal to the number of times it is left that particular vertex. So, since these are equal and together they account for the total degree of any vertex, we automatically get that the vertices must have an even degree. Every vertex must be of even degree. So, that concludes the proof of Euler's theorem. Okay. Now, the next thing that we will learn today is another kind of walk or a path on graphs which are called as Hamiltonian cycles. So, we will first define what are Hamiltonian cycle. A Hamiltonian cycle is a cycle in which every vertex of the graph is visited exactly once. It is a cycle in G. So, we are talking about Hamiltonian cycle in a graph G. Okay. So, of course, the natural question to ask is, given a graph, does it have a Hamiltonian cycle or not? So, we will see some examples. So, if you take the complete graph on n vertices, okay, this of course has many Hamiltonian cycles. You can start at any vertex, okay, and go to any other vertex in this particular graph. So, complete graph on n vertices, this is here the value of n is 5. So, k phi has a Hamiltonian cycle. If you look at, let us say, the cycle graph, this is also a graph which contains a Hamiltonian cycle. Whereas, if you take this particular graph, this does not have a Hamiltonian cycle, because the vertex, let us say if we number this as vertex 1, if you start at vertex 1, you can never end up back at vertex 1, and if you start at any other vertex, the moment you reach vertex 1, you are stranded there, okay, and therefore, this is a graph which does not have a Hamiltonian cycle. So, in these examples, it was easy to see whether it contained a Hamiltonian cycle or not. Unlike the Eulerian cycle problem, Hamiltonian cycle problem is not very easy to solve. So, we will see a particular example. So, we will again look at our Peterson graph. So, this is a graph on 10 vertices. So, this is 10 vertices and 15 edges, and we want to know whether this graph contains a Hamiltonian cycle. You can look at the graph stare at it for a few minutes and figure out if it does contain a Hamiltonian cycle. If it does not contain a Hamiltonian cycle, what we have to show is that no matter how you walk in this graph, you can never start at a vertex and reach back at the same vertex after visiting every vertex exactly once. Okay. So, in fact, that is what we will show, that this graph does not have a Hamiltonian cycle. Peterson graph does not contain a Hamiltonian cycle. Why is that the case? I will prove this claim via a very crucial observation about Peterson graph. So, let us call this Peterson graph as G. So, first claim is G does not have any 4 cycle. Okay, this is a crucial fact that we are going to use. Okay. Now, how do we see that this is a graph without 4 cycle? Okay. Now, if you look at this graph carefully, you will see that there are 2 cycles in this graph, each of length 5. There are many 5 cycles, but you can see that there are these outer pentagon and the inner star, which also can be drawn as a pentagon. Okay. So, if I number this as 1, 2, the outer ones is 1, 2, 3, 4, 5 and the inner ones is 6, 7, 8, 9, 10. So, you can see that 6, 7, 8, 9, 10 also forms a cycle. So, 1, 2, 3, 4, 5 is a pentagon or a 5 cycle, and 6, 7, 8, 9, 10 also form a pentagon. Now, these cycles, I mean, if you consider just these cycles, there are no other edges between them. For example, between 1 and 3 there is no direct edge, between 5 and 3 also there is no edge. So, these cycles are 2 disjoint cycles, and they do not have, if you just restrict the graph to those vertices, there are no smaller cycles in it. Okay. So, if I look at the graph consisting of just vertices 1 to 5, they do not have a 4 cycle, and if I restrict to the graph to vertices 6 to 10, they also do not have a 4 cycle in it. And therefore, we can say that if at all there was a 4 cycle, it should have edges which go from cycle 1 to cycle 2. There should be an edge, any 4 cycle should have an edge which goes from the outer circle to the inner circle. And outer circle to inner circle, the edges are, I am going to draw that in red. So these red edges, at least one of these red edges must be present if there is any 4 cycle. Okay. That is, if there is a 4 cycle, then that 4 cycle must contain one of these red edges. Without red edges, it is impossible to have a 4 cycle. What we will show is, even with the red edges, there is no chance of having a 4 cycle. So let us say that one of these red edges is there. All the red edges, you can see that from the symmetry we can assume that all of them are of the same kind. So if there is a 4 cycle involving one of the red edges, then certainly there are 4 cycles involving any other red edge as well. That is from the symmetry of this diagram. Okay. So let us say 5, 6 is an edge which is there on some 4 cycle, 5 to 6. Okay. Now 5 to 6, from 5, if there is a 4 cycle, there are only 2 possible edges, 5 1 and 5 4, and from symmetry again we can say that we can just look at 5 1. Okay. So if there was a 4 cycle, 3 of its vertices are already in place, 5, 6 and 1. Okay. And if there is a 4 cycle, 6 and 1 should both be connected to a common vertex, and you can see that there is no such vertex. 6 and 1, there is no other vertex such that that vertex is connected to both 1 and 6, and since there are no other, so that is, you can't have a vertex x such that 6x is an edge and 1x is an edge. So that basically means that Peterson graph does not have any 4 cycle. Okay. So how is this fact going to help us show that Peterson graph does not have a Hamiltonian cycle? So at the moment we have shown that the graph G, or the Peterson graph, does not have a 4 cycle. We need to show that G does not have any Hamiltonian cycle. Now suppose G did have a Hamiltonian cycle, we can say that all the vertices could have been traversed in a systematic manner. So let us say the ordering of the vertices is V1 to V2 to V3 Okay. So there is some ordering of, we can just place these 10 vertices. So I do not know whether V1 is the vertex 1 or V2 is the vertex 2 and so on, but there is some order, in some way in which you can traverse all of them. Okay. So let us assume that the starting vertex is V1. Okay. Now this accounts, I mean, if you look at these 10 cycles, that accounts for 10 of the edges in the graph. Okay. Now we can think about what are the other edges present. Okay. Just look at the Hamiltonian cycle if there was one, okay, and let us just draw it, and we will get a cycle consisting of 10 edges, and there are 5 other remaining edges which we have to add to this to get our original graph. Okay. Where all can we add that edge? V1 is an arbitrary vertex. Okay. If we had a Hamiltonian cycle, surely there is one starting at any particular vertex. Could have, so because you look at the cycle, start at look at any particular vertex in the cycle, start at that point and traverse, you will get another Hamiltonian cycle. So if you have one Hamiltonian cycle, you can have the Hamiltonian cycle start at any particular vertex. So we can assume that V1 is equal to vertex number 1. Okay. Now from V1 there are 3 edges, 2 of them have already been accounted for. The third edge must go somewhere. Where all can it go? Okay. So here we have shown that G does not have a 4 cycle. It is apparent that G also does not have any triangles. Okay. if you take any 3 of them, they are not going to be form a triangle. So, G does not have any 4 cycle or 3 cycle. So, V1, let us say V3 or V9, that would make a triangle in the graph, but the graph does not have a triangle. The same applies if you connect it to V4, because then you will have a 4 cycle, and the same applies if you connect it to V8. Okay. So, now the only 3 options are V1 could be connected to V7, V6 and V5. Okay. So, V1 we can think of V6 as the diametrically opposite vertex. Okay. Note that all of these vertices 1 to 10 has one edge missing from there, okay. And together there are 5 edges missing. Now, can it be the case that every vertex is joined to its diametrically opposite vertex along this particular path? By diametrically opposite, what I mean is V1 and V6 are diametrically opposite, V2 and V7 are diametrically opposite, V3 and V8 are diametrically opposite, and so on. Okay. So, can every vertex here be joined to its diametrically opposite vertex? If that was the case, V1 is joined to V6 and V2 is joined to V7. Okay. If every vertex is joined to its diametrically opposite vertex, then this is what would have happened, but that automatically creates a 4 cycle V1, V6, V7, V2. Okay. So, this is not possible. So, there is at least one vertex which is not joined to its diametrically opposite vertex. Okay. So, we may assume without loss of generality that that one vertex is V1. So, V1 we may assume that V1 is joined to one of V5 and V7, and these are symmetry cases. So, we will just say that V1 is connected to V5. Okay. So, we can assume without loss of generality that V1, V5 is an edge in the graph. Okay. So, our starting point was we assumed that there is a Hamiltonian cycle, and we somehow argued that Hamiltonian cycle has missing edges, and if you look at the starting vertex as 1, its missing edge is goes to vertex V5. Okay. So, this is part of the graph. There are other edges also. So, if you look at vertex 6, where all can 6 be connected to? Okay. We argued that V6 and V1 are not connected. So, there are other possibilities, but we will see that if you assume, based on our claim that G does not have a 3 cycle or 4 cycle, we cannot connect 6 to any other edges. Clearly 6, 8 and 6, 4 are ruled out because of 3 cycle. V9 and V3 are ruled out because of 4 cycles. So, 6, 8, 6, 4 causes 3 cycles, 6, 9, 6, 3 causes 4 cycles. So, they cannot, because V6, V9, V8, V7 forms a 4 cycle. So, the only remaining vertices are, so V7, V5 anyway are connected, they cannot be considered. So, 7 and 5 ruled out, 7, 5 and 1 are ruled out. Okay. So, the only remaining vertex is 10. If you look at 6, 10, you again have a 4 cycle. Okay. 6, 10, 1, 5 forms a 4 cycle. So, this also causes a 4 cycle, and therefore, we cannot have any edge out of 6. So, that contradicts our initial assumptions that there is a I mean, if we have this particular edge, we looked at the Peterson graph, surely there is an edge between 6 and 10, I mean 6 and some other vertex. We argued that 6 cannot have any outgoing edge other than B7 and B5. Okay. So, by this argument we could show that Peterson graph is a graph without any Hamiltonian cycle. Okay. So, this required careful examination of many of the properties of Peterson graph. We could not have a, we did not have a general result like we had in the case of Eulerian cycle, wherein we told that we just have to look at the degree of each vertex. If each vertex is degree 2, then automatically every connected such graph is going to have an Eulerian cycle. Okay. So, now we will move on to some different notions. So, we learned about cycles, we learned about two different types of cycles, Eulerian cycle and Hamiltonian cycle. The next special kind of graphs that we will look at is what are called as trees. Okay. So, trees are graphs which is two crucial properties. Okay. So, let us call it by T. So, T is also, this is a graph. First requirement is T should be connected. The second requirement is that T should not contain any cycle. Okay. So, let us see some examples. If you look at this graph on 6 vertices, this is called as a star graph. So, this graph does not have any cycles and it is a connected graph. The line graph, this is also an example of a tree. If you look at the wheel graph, this is not a tree because there are many different cycles in this graph. You can have trees of different kind. So, this is an example of a rooted binary tree, root because we will usually, I mean when we draw it like this signifies the root, and binary because every intermediary node has 2 children. We will study about those things later, but you can see that this is a graph in which there are no cycles and that it is a connected graph. So, these kind of graphs are called as trees. We will see some crucial and simple properties of trees. In a tree, let T be a tree. First fact is there is a unique path from any vertex V to any other vertex U. Okay. So, choose 2 vertices, between those 2 vertices there is a unique path whenever the graph is a tree. We will prove all these facts. The second fact is T has n minus 1 edges, where n is the number of vertices. The third fact is removal of any edge results in precisely 2 disjoint trees. Okay. So, if you take a tree and remove one edge from it, you will get another graph which will have 2 connected components, and both those connected components will itself be trees. Okay. So, we will quickly see a proof of these facts. Okay. So, you look at any particular vertex u and any other vertex v, we want to say that there is precisely one path between them. Okay. So, we may assume the contraries, that is, let us assume that there are more than one path between u and v. So, let us say this is some path and then there is some other path. Okay. So, if you look at these two paths, there is a first place where these paths diverge. These paths start at the same vertex and end at the same vertex. So, clearly there is some place at which these paths diverge. Okay. So, let us say this is a point at which they diverge, and then of course, they will come together at some place. So, if you call this first point as I, and then there is surely a first point after I where they come together, because surely they come together at V. So, they must come together at some point, and the first place where they come together, let us call that as J. Okay. So, in between I and J there are no common vertices. Okay. The paths do not have any other common vertices in between I and J. So, these are all edges in the graph. Now, if you look at vertices I and J, and if you start walking from I to J along the path 1 and then from J to I along the path 2, that is basically a cycle in the original graph. Okay. So, if there are two paths, then surely there is a cycle in the original graph. There are more than one path. We can engineer a cycle in T. Okay. Because by looking at these two paths, we can say that there will surely be a cycle in the original graph. And the original graph, by virtue of it being a tree, we know that it cannot contain any cycle. Okay. So, this cannot be the case that there are more than one path. So, there is at most one path. How do we say that there is at least one path? Well, because this is a connected graph between any two vertices, you can go from one vertex to another vertex. Okay. So, that proves statement 1 that there is a unique path. Okay. We will now prove statement 3 that removal of any edge results in two disjoint trees. Okay. How do we show this? Well, let us look at one particular edge u comma v. So, there is a direct edge between u and v. Suppose we remove this. Okay. Now, look at all the vertices which are connected to u and all the vertices which are connected to v. Now, after removal of this edge, there cannot be any third kind of vertex which is neither connected to u nor connected to v, because if there was one such vertex, then it is not connected to either u or v in the original graph, and therefore, we can argue that every vertex in the original graph either belongs to this set SU or SV. Okay. Now, if you remove UV, SU and SV are not going to be connected. Why? Because if they were connected, then it would mean that from U to V there is more than one path. Okay. Because U to V there is a direct path, and if SU and SV were connected by some other thing, clearly by virtue of any vertex being in SU, there is a path to U, and here there is a path to V. So, you can go from U to this particular vertex U prime, and from U prime we can go to V prime, and V prime we can go back to V. So, that is an alternate path, but by our first fact we know that there is at most there is exactly one path. So, we can argue that SU and SV are disconnected components. Okay. and by virtue of this being connected to, all this by definition is all those things which are connected to U. So, that is a connected part, and of course, there is no cycle in SU. If there were cycle in SU, then there is a cycle in the original graph. So, this is a cycle free connected part, and therefore, that is a tree, and this is also another tree. So, we know that the removal of any edge results in exactly 2 disjoint trees, and now we can prove the third fact that that any tree has at most n minus 1 edges. Okay. So, if you take any tree with one vertex, clearly there are no edges in it. So, the base case would be that we are going to prove the statement by induction, and the induction hypothesis would be true for a graph with one vertex. Now, you take any other tree, suppose it is more than one vertex and surely it should have an edge, remove that particular edge. So, take any tree T, okay, and if the number of vertex is greater than 1, then surely there is at least one edge. So, and remove any of those edge, and then we would get two components, let us say SU and SV. SU is a tree, and therefore, the number of edges by induction, SU has size SU, or when we write size SU, that means the number of vertices in that particular component minus 1 edges, and SV has size SV minus 1 edges. So, together the total number of edges, that will be SU minus 1 plus SV minus 1 plus 1 for the edge UV that we had removed. So, that would be size of SU plus size of SV, that will be n minus 2 plus 1, which is equal to n minus 1. Okay. So, any tree will have exactly n minus 1 edges. Okay. We will just define something for later. So, there is a notion of forest. A forest is just a collection of trees which are disjoint. Okay. So, if the collection had k disjoint trees and the total number of vertices was n, then we will have n minus k edges in it, okay, which can be proven by the by using fact 2 repeatedly. Okay. We have just one connected component, the number of edges was n minus 1. Okay. We will start off with the next topic, which is known as coloring. Okay. So, we will define what are called colorings. So, we have a graph and then we want to color the vertices, and what is a valid coloring, that is what we will first define, and then we will look at a simple algorithm to color a graph. Okay. So, let us formally define what is a coloring. A coloring is basically a function from vertex, this vertex set to natural numbers. Okay, this is a set of natural numbers. And this function, so any function from the vertex set to natural numbers is called as a coloring if it satisfies certain requirements. Okay. The requirement is Cx should not be equal to Cy if x comma y is an edge. Okay. Although we are writing it as an ordered pair xy, since we are looking at undirected graphs, they essentially mean the set x comma y. Okay. So, each vertex is being assigned a number, and for vertices which share an edge between them, they should be assigned different numbers. So, let us look at our Peterson graph. If we give, let us say, a red color to this particular vertex, then vertices 2, 8 and 5 cannot be given red color, they should be given a different color. Okay. So, these colors you could assign them as numbers, So, this should be a different color. 8 can be the same color, there is no problem, because there is no edge between 2 and 8. Okay. So, we can color it this, I mean these vertices can be colored in this particular manner, and then 10 can be given red color itself, 7 can again be given red color, but 6 cannot be given red color because 6, 7 is an edge and it cannot be given yellow color. So, it should be given some other color, blue color, let us say. And now, if you look at vertex 9, that also can be given blue color. Okay. Because 9 is not, I mean the vertex 9 cannot be given either red or yellow. And if you now look at vertex 4, that can be given red color, and vertex 3 can be given blue color. Okay. Vertex 3 cannot be given red or yellow because it has neighbors which is colored with the same color. So, here we can see that Peterson graph can be colored using 3 colors. Okay. If you say red is 1, blue is 2 and yellow is 3, you get a function from the vertex set to natural numbers. So, that is the notion of coloring. Clearly, if you have n vertices, you can surely color it using n colors, and if you take the complete graph on n vertices, you would require n colors. But what we are interested in is, if you are given a graph, how do we determine the minimum number of colors required to color the graph, okay, and that we will define that particular property. The least number of colors required to color a graph G is called as the chromatic number of the graph, okay, and this is denoted by chi G. Okay. So, what we are interested in is, given a graph, how do we determine its chromatic number? This is a difficult problem. For arbitrary graphs, finding an algorithm which will determine this is not a easy task. But we will look at a greedy algorithm for coloring, and we will say that the chromatic number is going to be certainly less than some quantity. Okay. So, we will basically prove the following theorem. Suppose the maximum degree in G is k. That means, if you look at any vertex, the maximum degree that it has amongst all the vertices, the vertex which has maximum degree has degree k, then chi G or the chromatic number is less than or equal to k plus 1. That is the first statement. The second statement says, if G is connected and not regular, then chi G is less than or equal to k. Okay. Not regular means, so we will first define what are regular graphs. So, a graph is called regular if every vertex has the same degree. If you look at our Peterson graph, look at every vertex, its degree is exactly 3. So, this is an example of a 3 regular graph. So, if it is not regular, then it will require less than or equal to k. If you look at the cycle graph, every vertex has degree exactly 2, and since the degree of every vertex is exactly 2, chi G is less than or equal to 3. That is what the first statement says, but this is an example of a graph which is regular. Okay. If you had taken some other graph where the degree is at most 2, but it is not a regular graph, then you can argue that you do not require more than 2 colors. Okay. So, the proof of this theorem will be via an algorithm. So, we will show that the greedy coloring algorithm will correctly color the graph without using more color. Okay. So, what is the greedy coloring algorithm? So, the algorithm is very simple. So, let us describe the algorithm systematically. So, choose an order on vertices. Okay. So, let us say you are going to examine vertices in this particular order V1, V2, Vn, and color of V1 we will assume it to be 1. Okay. And at any stage, suppose you are coloring the ith vertex. Look at the least number that can be assigned to that without violating the coloring property. Okay. So, look at the vertex I and look at its neighbors. So, they would have got some color, okay, and you can choose for I the color which is least amongst the acceptable colors. Okay. So, acceptable colors would mean any number which is not a color of its neighbor. So, such that ith color is used by a neighbor. Okay. So, consider the set of colors that the neighbors have already used and remove those colors from natural numbers, and whatever is the least remaining color, that would be the least amongst the acceptable colors, and that is the color that you choose for I. Okay. This is the greedy coloring algorithm. Okay. So, now if you look at the greedy coloring algorithm, whenever you are examining a particular vertex, since it has at most d neighbors, if you look at 1 to d plus 1, okay, if you look at the set 1 to d plus 1, amongst these numbers at least one number would be missing, and that number can surely be chosen as a color for I. Now, we are using only colors from 1 to d plus 1, and using these colors you can color the entire graph, and therefore, the greedy coloring algorithm finds an acceptable coloring where you do not use any color greater than d plus 1. Okay. The second part of the theorem states that if you have a connected graph which is not regular, then you can color it with less than or equal to k colors. So, the max degree is k, and if the graph is not regular, then k colors suffice. Clearly, if the graph was regular, then we cannot guarantee that it will be colorable in k using k colors. Okay, for example, if you take the pentagon, which is a 2 regular graph, we can see that we require at least 3 colors. But if you look at, let us say, the square, this is a 2 regular graph and it can be colored with 2 colors. So, the second condition just states that if you are guaranteed that it is not regular, then you do not need more than the max degree number of colors. So, let us prove that part. Again, we are going to use our greedy coloring algorithm, and what we will do is fix the order in which the vertices are to be colored. So, we want to fix the order of vertices V1 to Vn. We will start describing this by first stating what is Vn. Okay. So, what we know is that max degree is equal to k, and this is not a k regular graph, this is not a regular graph. So, if it is not a regular graph, then it means that there is at least one vertex whose degree is less than k. So, we will choose that vertex as Vn. So, Vn is the vertex of degree less than k. So, there is a vertex whose degree is strictly less than k, and we will take that vertex as Vn. So, if you take Vn, it is going to have lot of neighbors in the graph. So, suppose this is your graph G and Vn is this particular vertex, it is connected to some other vertices. Okay, there can be at most k minus 1 of them. Okay, we first write all of them, okay, in any order. So, Vn minus 1, Vn minus 2 up to Vn minus r. So, only requirement is r plus 1 will be less than k, okay. And then we will take Vn and look at neighbors of Vn. So, write down the neighbors of Vn minus 1. So, these are neighbors of Vn minus 1, and then we can write down neighbors of Vn minus 2 and so on. Okay, sorry, this is the first block is neighbors of Vn and the second block is neighbors of Vn minus 1 and so on. So, of course, when you are writing neighbors of Vn minus 1, if you have included, if there are some common neighbors with Vn, you do not include them. So, all the fresh neighbors of Vn minus 1, the neighbors which has not been included so far is included into this block, and you do systematically. Since it is a connected graph, this will list out all the neighbors, and finally you will get V1. So, if you look at the vertices in the order V1 to Vn and apply greedy coloring in this particular order, we can argue that we do not require more than k colors at any point. The reason being, look at any vertex that you pick, okay, let us say Vi is some particular vertex, one of its neighbors is somewhere ahead, okay, there is at least one neighbor which is further ahead, except for let us say Vn. Vn does not have any neighbor ahead of it, okay, all its neighbors are would have appeared previously. So, if you take Vi and look at all its neighbors, since at least one of the neighbors is in front, the number of colors used by the greedy coloring algorithm to color the neighbors of Vi would be at most k minus 1, okay, because Vi, degree of Vi is going to be less than or equal to k, but amongst these, since at least one neighbor is in front of Vi, it comes after Vi, we know that the colors so far used will be strictly less than k. So, there is at least one color left amongst colors 1 to k, and that color can be used for Vi. Of course, this argument does not work for Vn, but Vn we are anyway guaranteed that its degree is less than k, because that is how we chose Vn. So, even for Vn, we will have a color left with when we are coloring via the greedy coloring method. Okay. So, that concludes the proof.